Thank you very much, Jason, for passing that over. So at this point in the presentation, we're going to be going through a live demonstration, excuse me, as to how PCI's Geomatica software can be used in an operational environment in order to perform and produce some of these change detection images and identify point targets, particularly, which is a specific military application. So just to give you a little bit of background of this demonstration and what we're going to be presenting today. We're going to be looking at polarimetric change, so also known as PCD. So it's polarimetric change detection with a focus on identifying point targets that have changed either in structure, in shape, or just completely been removed from the equation. So we're going to be using RadarSat-2 quad pole fine beam coherent data sets. We're going to be looking at two sets of dates. So we're going to be looking at May 3rd, 2010 and May 27th, 2010. But we're also going to be looking at May 27, 2010 and June 20th. Now we decided to work with coherent data sets in this demonstration, but all the analysis in which I'm going to perform does not require that you work with coherent data sets. You can work with data sets that are temporally closer together, but are not coherent, and all they require is the use of Geomatica, for example, ortho engine, in order to co-register the two images in order so that change detection can be applied. So the actual type of demonstration, what we're going to try to produce here is a product where we're not only identifying changes in objects and structure, but we're also going to be identifying what exactly has changed. But we're going to be focusing on smaller points in objects. So we're going to be trying to discriminate fields in larger objects, which we know may change due to a growing season. But at the same time, we don't want to include that. We don't want that to be interfering with our analysis of identifying, say, vehicles or large vehicles that have either moved or even buildings that have moved place. So we're going to be focusing on smaller points. But then lastly, one of the things we're going to be showing how Geomatica has very useful tools for actually extracting this information and then taking it from just imagery and identifying points in a raster, but extracting the polygons so that they may be used in a map for later analysis. So just to give you an idea of the study area, we're going to be focusing most of our analysis around the Ottawa airport, which is in the southern portion of Ottawa. So right here is Ottawa for Ottawa, Canada, and we're going to be focusing most of our analysis on here. Now this is a clipped image of a RadarSat, but this analysis can be applied to a larger area so that it covers the entire scene, or it can also be focused on a smaller region depending on your area of interest. So lastly, one of the things I wanted to just discuss, and this is also a very important slide, so as Bill mentioned in his presentation, this is sort of a surveillance strategy that can be used to help operationalize SAR data. Now one of the problems with SAR data in the past is that it was very difficult to analyze, and turnaround time to turn it from a raw product into useful information was very difficult. But now using tools such as PCI Geomatica and advanced RadarSat data, it's very possible to take this information and turn it around in very minimal amount of time so that you can have useful information on the field. We're going to show you some automated techniques that can be applied in order to extract this information in a user-friendly manner. And what we're also going to be showing is that you do not need to be a SAR expert in order to work with SAR data. You just need the right tools. So the first thing we're going to be focusing on is just the imagery itself. So as mentioned, we're working with coherent data sets, so there is a bit of a time lapse between the two data sets. But I'm just going to show you very quickly what coherent data is and why it's important. So coherent data, for the most part, is used as a means for identifying changes in phase. So if we look at this data set here, and we focus on certain areas, we can actually see between two data sets that are coherent. So if you look at the top two that my mouse is clicking on, these are two coherent data sets. And what this is basically the satellite is in the exact same position in space when it captures these images. So not only is it in the same position, but it's also got the same incident angle or viewing angle, and it's looking at the exact same point using the same beam mode and everything. So pretty much all factors are the same except for what might have changed on the ground. But one of the nice things about coherent data is that it pretty much comes co-registered. Now there might be some minor offsets between the data sets, but Geomatica includes intuitive tools in order to just simply apply a very quick offset. So there's no resampling, which means that phase detection or phase change detections can still be applied. So I'm just going to, so if you see here, as I toggle this top image on and off, you will notice that the imagery itself is very accurately co-registered. But the moment that I go from one coherent data set to the next, you should notice a significant shift and reforming of the imagery because it's being captured from from the satellite at a different point in space, different viewing angle, and at times it can even be of different beam modes. So it really is important that if you're doing phase change detection or phase analysis, that you consider that you use coherent data sets. Now, for the analysis that I'm going to be showing, I just want to reiterate that it's not important that that you're using coherent data set. You can use data sets such as the 28 and 31, which I'll toggle back on. Even though it is a misalignment, you just need to use Geomatica's ortho engine or some of our tools in order to get the proper co-registration. So that's just an introductory to the data set that we're going to be working with. So I can go back to my slide very quickly. I'm just going to show you the next step. So what we want to do is we want to take this raw products, this data, and we want to produce some daily products from it. And so at this point in this presentation, we're going to be showing you production of coherent amplitude change products as well as polarimetric change products. And these two different data sets, these two different types of change analysis, tell us two different things. The coherent amplitude change products tell us whether an object is present in the first image and no longer present in the next image. But sometimes these objects, what happens if the object changes or the structure of the object changes, or even if the object's been replaced by another object that has a strong return? That may not show up in the coherent amplitude change, but we still would like to know about that. So that can actually show up in the polarimetric change products. So as I mentioned before, is that if you're working with SAR data in an operational environment, you need a quick turnaround time. You don't have time to do extensive analysis. So PCI has essentially taken these tools or created tools rather that makes this kind of analysis very simple and easy to provide, or easy to perform. So what I'm bringing up here is an example of two models that I have that basically calculate all of the polarimetric parameters or polarimetric discriminators. So this model on my left over here basically is a simple model that ingests the SAR data directly, and then it actually creates the different polarimetric discriminators and then writes them all to a single output file. On my right here, we have another model which basically extends this first model. So it takes the polarimetric change, so the outputs from this first model, and then it runs it through our change detection modules. So before I go and show you some results, I just want to quickly spend a little bit of time discussing what is required. So just to show you how simple and easy it is to set up these models. And once again, I'd also like to just mention that I separated these two models for simplicity of presenting the information, but these could be provided as one larger model. So to import SAR data or RadarSat data using Geomatica, it's a very, very simple process. So we simply have to browse to the file that we're working with. Sorry, one second while I find it. So we can go into our raw RadarSat products here and then basically choose the product.xml file. We open that, and then we have the option of applying a data calibration, which for any type of change detection is absolutely essential. So it's important that you apply the same data calibration for all the data sets that you can be running through the change detection. Now, to make it even more simple and more automated, we have the option of doing batch process flows. So we can actually load multiple projects and then run this entire process for multiple images all at one time. So then what's the next step? Well, the next step is that it has to run through a filter, which there's really no setup for. You can choose the filtering size and the number of looks of your input data. But then once it's been through that filter, we basically are computing our different polarimetric discriminators or parameters. So to give you an example of one, if I click on that, all we need to do is choose the input file and then choose where our output file is going to be written to. There's really no setup at all, and for the most part, the other modules for computing polarimetric parameters are the same. There's really no setup. So it's very nice to work with. Now on the other side here, once we have our final product, or once we have our polarimetric products, we can then run it through the change detection. So change detection actually looks at two different things. So it provides you with absolute change metrics, but it also provides you with the relative change. So what the relative change is basically how much the pixel has changed relative to all the other pixels within that data set, and it's ranked by percentile. So it makes it very easy to identify the major changes within an image. So once again, the setup is quite simple. You choose your input data, so a test data set. Now that is your later image, so the after image. And you have a reference data set, so this is the before image. You point them both to the module. You have the option of running filters, but if you already ran a filter earlier, it's not necessary. Actually, it should not be run in that case. And then you point it to an output file. That's all there is to it. And once again, this can be set up in a batch process. So that's the models. Now, what does this produce? Now, the models themselves produce these two different products. So the first model that I showed you, and this is why I broke it down into two different models, is that it's providing the polarimetric parameters. So we essentially get a file here where we have all of our output polarimetric parameters. So each module will produce 4 different channels. So for example, these 4 channels, and it's going to show you the first channel will be the test image, just a simple copy of the test image. Then the second channel is a simple copy of the reference image, so you have them as references. But then we actually get the last 2 channels is where we get our metrics and our changes. So the first one is just a logarithmic change metric, so it's normalized. And then the second one is a ranked change metric based in percentiles. So what this produces here is basically a change image. And I know that there's probably a little bit of lag over the internet, so I want to just hold off before I move too quickly. And it basically produces an image like this. So I've loaded the change image, or the ranked change image, so it changes in percentiles, on the screen here, and it's based in a pseudo color. So what we can extract from this is that the areas in red and purple or white are areas of high change, so high relative change. So if I click on this pixel here where it's very purple or quite dark, and we look at the pixel value below, you can see that it says 97.5. That means that that pixel had a significant amount of change, more so, or that it was in the 97th percentile of this entire image, or of all the change that occurred in this image. So it makes it very easy to identify areas where they've changed. Now this is only part of the story. See, at this point we can identify everything that's changed, or the largest degree of change, but it can be difficult at this point to identify the specific point targets. So we want to omit these fields, and we want to just focus on point target changes. So if I'm going to remove this image here from the viewer and focus on the underlying image, and I'll let that load. I know that it might take a couple seconds to load on everyone's machine. Actually, I believe I have a way of tracking the lag. And I think that's about 90% of the people. It should have loaded now. So what we can take from this image is this is basically an RGB image, or a pseudo-color image in a way, where we're looking at the before image, the after image, but we're also looking at the ranked change image. So what this actually shows us is it helps us to visualize the point target changes, so in where man-made features may have been taken away or added. So if we look very quickly, we have areas in purple or red is basically identifying areas where the change has, or an object has been removed. Areas in blue or cyan, not blue rather, but cyan, is identifying areas where objects have appeared, or vice versa, sorry. So one of the things that we've basically done is that we've loaded, because the change image is loaded in the blue band, the before image is loaded in the reference image, or the before image is loaded in the green, and then the after image is loaded in the red band. We can use this information to identify point targets of this nature. Now these fields in blue that are quite prominent are basically field changes, so they're not object changes or new man-made features. These are changes in larger fields, for example, growing season. So between the two images, these fields have grown as they're taken in May, and so it's identifying this as a field change, whereas these other more yellow areas have not grown because these are forested areas, so they have not changed much. They're not identified as change. So I can discuss this a little bit later on. So just to go back to where we are, just to provide a little bit of a sense of reference. So we took a look at the different types of imagery that we can work with and the types of imagery that in this demo we are working with. Then we moved on to the daily products that we're producing. So I showed you that I showed you basically the results of the change product, so the coherent amplitude change and as well as the polarimetric change. So we were looking at a variety of different changes there. Now the next step and the final step is to extract this information, to turn this into daily intelligence. So basically actually extract those polygons so they can be added to a map for later use or use from another or in operations. So we're going to be looking again at extracting point targets whether their presence has changed, so if they're there in one image and not in the other. But we're also going to look at whether or not the structure or the object itself has changed. So this will help us identify features that have been removed, but say replaced by something similar but has a different shape or structure to it that may not show up in the amplitude change. So I'm going to be showing you this product. So this is basically the results of our extraction. So what is required to do this is basically you can use our modeling program as well, or our scripting language, in order to basically set some simple conditions. But then we can use a very powerful tool in Geomatica, which I'm just going to show you quite quickly, which allows you to extract information based on spatial dimensions as well as spectral dimensions, or in this case digital number information, in order to extract them and convert them into polygons for use on a map. And I will describe this image in detail. I know you see a few colors there, but I will just come back to it in just 1 second. So Algorithm Librarian includes this amazing new tool which is included in our Geomatica 2012 release, which is called XPolRAS. And I've pretty much since this tool has been introduced in our software, I have used it for almost every project I've worked with. So it's a very, very, very useful tool. So what this tool allows you to do, as I mentioned, is it allows you to choose a raster layer and then extract polygon information based on some different thresholding techniques. So we can choose our minimum and maximum DN value or pixel value. We can choose our minimum and maximum area, which that was the main use of this. Our identifying just point targets was done using conditional statements, but then we used the minimum area and maximum area to just make sure that we're extracting only point targets, nothing too large or nothing too small that it might be considered noise at this point. So from that, we're basically able to produce, oh, actually one last thing is that we can also choose compactness. So we can only extract linear objects, or we can focus on more round or compacted objects. So another very valuable asset or tool to the whole Geomatica tool set. So from this, what we're able to produce here basically is a map where we're able to look at different degrees of change or different types of changes. So just to provide a little bit of reference to these colors, the image that we're looking at right now is our before image, so the one from May 3rd, and certain colors or certain objects have been color-coded to mean different things. So if we focus on certain areas, we can see that there is so for example, green means that there's a structural change and it's gone from man-made to natural. So it means something's been removed or a man-made object has been removed. The red, so this more red color here, is identifying once again structural change but in the opposite direction, going from natural to man-made. So it means something new, a new man-made object is now present there. And then in yellow here, we're just looking at the absolute power return to see if things have changed. So yellow objects here are identifying whether or not an object has appeared in the new image, and then blue is whether or not objects have disappeared. So I'm just going to show you some of the accuracy of this very quickly by toggling between the two images. So if we want to focus, for example, on a point over here, so what we can see by this point, which is quite interesting, is that if we focus in here, we can identify that on this point it's identifying it as both structural change from natural to man-made. It's also saying an object has appeared. So if I turn those two layers off for now, we can see that there's nothing there in the before image. Remember, those objects were identifying it as new objects have appeared. But if I toggle off the top layer, we can see that there's now an object there that have been nicely identified by both of these different parameters, or both of these different change detection options. So that is just one of the power, and as we can see even throughout the airport, we can see areas where planes are parked and have moved. We can see a variety of different changes, but notice how the airport terminals themselves are not being identified. So very, very cool tool, very, very capable of extracting information with minimal to no manual digitizing, which makes it very, very powerful. So without further ado, I'm going to pass it over to Jason again.